So today I will actually be having this video in two parts, or technically three. At the beginning, I'll walk you through from a blank canvas on how to build a soft actuator from scratch, one that just has pneumatic chamber and tendons. Then I will go through the examples that we've shipped in our repository, the first one being a Continuum arm and the second one being a pneumatic gripper. And for those, I'll just briefly go through and point out based on what we learned in the first section so that you can understand how to make adjustments as needed. So once you have Grasshopper open, we can go ahead and start a new document. And this first part will be a little tedious. We just need to start putting out some variables. I'm just going to drop down a couple number sliders for some of the things we'll be making, because for this we'll just be making, as you saw at the start of the video, sort of a bending pneumatic chamber that's just rectangular with two tendons for sort of steering left or steering right. So here I can just name in a couple of my parameters: length of 60, a width of 20, a height of 15, and then also need to set a thickness, and we'll also set a distance. So with that being said, then there will also be a couple of small expressions we'll need to be using, and I will just set those up here. Or this first one is just going to be dividing the width. So we have that center point, and then we need to have the internal dimensions as well. So for these, I'm just going to take the length and subtract it by the thickness, but I also need to do that for the width and the height. So I can call this Li for the internal length. I can set up the width minus thickness for Wi, the internal width. I'll drop down one more of those for the internal height. And if you have all of this in your Grasshopper, you'll start seeing it appear in your Rhino viewport. So some others, I need to get the middle of the height. So just going to have that here. I'm going to grab, I just need to take that center of the width and add some distance so that we can have sufficient offset from the center line for the tendons to actually give us some sort of steering or bending laterally in this example. Then what I'm going to do is I'm just going to clean up my canvas a little bit, especially whenever you're doing everything parametrically. It can get quite busy. And with that, you just want to make sure that everything is out of the way, or you at least know where everything is. Something that can be helpful with that is this wire hopper. I can just, it's a nice plugin that I'll link in the description that allows you to clean up some of your wires without it being too tedious. So as I go through this, of course, you'll need cushion installed. I'm going to first drop out this sofa body component before we start actually generating our body, so that we can have in mind what kind of things we need to be designing so that we can plug it in. But for now, I'll put that to the side and we can start with some construct points. We're mainly going to be using with construct points and 2-point boxes. So first, defining our body, I'm going to take a construct point and not change any value, so just at 0, 0, 0, and then at LWH to have the two corners, and then a box 2-point, and plugging in each of those points there. So here in our Rhino viewport, if I go into the perspective, you can see here now we start seeing some of the things we're making. And I'll try to keep everything pretty clean on the canvas so that it can be easier to follow along. But For the first things we'll need to plug in are the geometry as well as the body name. And with the sofa body, we will also need things such as the Young's modulus, such as the Poisson ratio and mass. So I'm just going to set that up here. We have an 80 kilopascals for the Poisson and for the Young's modulus. Poisson's ratio I'll just keep as the default, which I believe is 0.4. Set up my mass of 20 grams. And mesh size I will also just keep to 0.4. And this is actually what is going to be interfacing with gmsh for the volumetric meshing. So plugging in the body name is important so that we can actually have some of the data associated with this body. So I'm going to copy over these to construct points. And the first one, rather than 0, 0, 0, will be at -1, -1, -1. I'll plug that in. And then the other I will set up as 5, and then I'll do the width +1 and the height +1. So now I'm going to start clumping these up. So I'm just going to make a group and have this be my fixation and here for my body generation. And once we have that fixation, we can go ahead and plug it in to our sofa body component. And from there, we will want to set up some points that we will monitor. So again, grabbing that construct point, we can go ahead and have it 0, the center line at the width and the height, and then L, the center point of the width and the height. And I'm going to construct a 2-point line from here. If you do it correctly, you should see just a line across the top here. And because we're monitoring points, I actually have to divide that curve, plugging that in to monitor points, which sets up our initial geometry. For the body, we will also need to plug that into the visual geometry, because if we do not, then we actually won't be able to see the geometry. So this is monitor points, and then we can get started with our sofa cavity that I've dropped in here. So again, for that, we will be needing to construct more points. Essentially for the sofa cavity, I just want it slightly inset. So I can start it at, for example, let's say 8. Y is just going to be my thickness, and my Z is going to be my H mid. For the other, I'll just have internal length, the internal width, thickness. And what that ends up looking like once we connect a box 2 point is, you can see now we just have sort of this upper central half as a cavity. We can also see how the parametric aspect plays in. So, as we change the length, if we changed any of these things, it would adjust with the geometry. So for the cavity, there's a couple of things we need to plug in. First, the geometry. We will also plug in the channel, which is what is required for the pressures. And then we can go ahead and plug this in. Now, a couple other things that we'd like to plug in just to really show off the full extent. We can grab a sofa region, and what I'd like to do is just set up a simple strain limiting layer, or a layer that has a higher Young's modulus. So again, just going to go through construct a point. And here for the strain layer, I'm going to go from the X thickness, the Y thickness, and then keep the Z at 0, and then make another construct point. And this is where I'll have the internal length, the internal width, and then the thickness. And what this will look like is essentially just a 2-point box going from a very slim layer at the bottom. And keep in mind, with any of these, this can be geometry that you design in SolidWorks and just plug in as mesh files that have been pre-meshed. This is just really to show off the full parametric capabilities. So here, I'll plug in a Young's modulus of 2000 for the strain limiting layer here, then I want to actually go through and start creating some of my tendons. So with the tendons, we have to go ahead and construct points. Here, all I want to do is have these points slightly offset from the midline. So here I'll go maybe an X of 56. For my Y, I want to have that width center +1. Z, I can just have my HT, which here I didn't have. It's just going to be my thickness divided by 2. And my X here is 4. From here, I will need to do another 2-point line. You can see for this tendon, it's just slightly off center, and I'd like to make another one of those. The only thing I'm changing here now is going to be that offset rather than plus the D, it's going to be minus D. So here I just have these two on the two sides for my tendons. And here I have to divide curve, and something I want to point out here is that you'll notice I dropped down this merge component. Because of the way that the data is structured, it looks in a panel. If I connect it to the results, you can see all this data comes onto one branch. If you graphed it, it'll put them each on their own branch. Ideally, we want it so that each of these curves are separate. Rather than having the merge, we actually want to use the entwine component. And what this will do, if we plug in each of these, let me drop down a panel. Here, we actually see that now we have them on separate branches. And this works well. We can actually simplify and plug that into our points. And because we have the two, we have to go ahead and drop down a panel with multi-line data unchecked and plug that in for our second and third channels. And then the value type, we either have displacement or force. For now, we can keep it just as displacement. So we will be typing in millimeters for how much we want to pull. So now that that's all together, we can go ahead and drop down our next couple components. We will need our sofa run and sofa scene components for this. The sofa scene is where we'll be plugging in the body, but now we need to get into our profiles. So if we drop down to sofa profiles, this is what is going to actually be the protocol for commanding the cavity as well as the two tendons. So these channels that we had from before, we want to be able to plug them in here. So I can just drop down a panel and have 1, 2, and 3, making sure to turn off multi-line so that each of those are indexed. And then we will need to set up the times and the values. So here we want to be working with a tree because we have 3 different channels. So for this, how this works is it's basically just going to be keyframing when you want the actuation to occur. So I can do this by dropping down some panels, and for this, I will have it between 0, 1, and 2 seconds, plugging that in for all 3. And then I drop down another entwine, and this is what actually is going to be the commanding signal. So here, for example, I can have 0, 20, 20 if I want my cavity to go from 0 kilopascals at 0 seconds to 20 kilopascals at 1 second and maintain that for 2 seconds. Now, I need to make sure that everything is plugged in for the values. Right now, at the start, I can just have another of 0, 0, 0 so that it's just going to be the cavity that is controlling anything while the tendons just remain off. Now from this, we need to set up some of the files that we had, get my repository for the cushion clone that I had, the sofa folder, as well as the project file. And again, if you followed along in the installation video, this part should be something you're familiar with. These 3 paths are something you will need every time you work with cushion in Grasshopper. So set up the repository, and then you will also need a Boolean for writing to the scene. So we can make a Boolean toggle, just have it be true. And then for the run sofa, we need to connect to the scene path, connect to the sofa, connect the repository folder, and then a Boolean for actually running. Something else I'm going to do in this case is just add down a window size so that my sofa will always appear in the top right. So by having a panel with no multi-line, I can attach that there. And now if I go ahead and click run, we'll be able to see what is happening. So sofa appears, and you can see pretty fast, not much happened, as well as our camera was not really in a great position. So for now, we can close this and sort of diagnose what is happening. The main thing is the meshing. So right now we're plugging in boxes to the body, the fixation, and the cavity. What we really need to do is make sure that the mesh has proper fidelity. So I'm going to just drop down a quad remesh, as well as I need this quad remesh settings. And if I just attach it to the box, nothing happens. And that's because the box has to be made into a B-rep so that it can be meshed. So I can drop down a B-rep, connect it to the box, and then you can see from connecting it, I now have quite a nice mesh for my body. So I can plug that in for both the visual and the geometry, and you can see just by running that, I still don't have much, but you can see now the body is actually deforming how you might expect. Besides the fact that our cavity mesh is still very coarse. So here, going back into our cavity, you can see we're just plugging in the box, taking the 2-point box for the cavity, plugging that into a B-rep, and then plugging that into the geometry. Now, just by doing that, we can go ahead and run, and you can see now maybe something that you would expect more. Now with this, we have quite a lot of pressure, so you can see the mesh actually ends up exploding here. So what we can actually do is go through and change the pressure. So I'm just going to have it, instead of 0 to 20 kilopascals, I'm just going to have it 0 to 10. And here we can take a look, watch it deform, keeping an eye on, what the time is in the bottom left. And you can see now it doesn't explode, it just maintains that position. So we can close out, and now we can play around with a couple of other things. So for previewing what your sofa scene will look like, just by plugging in the sofa scene in the repository, as well as another Boolean to refresh, you can now see what the setup looks like, which can be very helpful for setting up the camera position. So all I'm doing here is I'm setting down some points, and looking at that preview, I'm just going to drop down a 3D point on one side for the camera position, and then I'd like to copy that over for the camera look at position. And by plugging that in, I can actually go ahead and run, and you can see now I have a much better view of how everything's looking. So closing out of that, a couple of other things we'd like to look at. Right now, our strain limiting layer is quite stiff. We can bump that down to 1000 and take a look. And really, cushion is meant for these iterative changes, all in silico, to really understand how your design choices are affecting the overall performance. We can also visualize the force fields as this deforms. And again, if you don't see the deformation you're expecting, most likely the material properties or the meshing is going to be the issue. So now for the protocol, we have our cavities. We have our cavity and our 2 tendons. So what I'd like to do now is have some control over the tendons. I'm just going to plug in pulling from 5 to 10 millimeters on one of my tendons. And from here, you can see I still have the pneumatic actuation, but now I have some out of plane motion due to that tendon, this green one that I'm pulling. So you can see it pulling here as that deformation occurs, based on the keyframes that I plugged into my SOFA profiles. So another thing I'd like to look at are the results that we actually get from this. So the SOFA results, if we plug that in with the body name that we had for our SOFA body, you can see it start to populate. All it needs is the repo path as well as a Boolean to refresh. So with this is, right now the points that you are seeing are those monitor points that we had throughout time. What I can do is I can take the last item in the index for these points, and what that will give me is basically just the tip position and connecting it to track points. You can see that tip position. Now, without the body, it doesn't really have much context. However, if I drop down a SOFA shape, what I would need to have is some non-zero integer connected to export shape, 10 for example. And what this does is that every 10 frames, it will save a visual representation of the body. So just connect the scene path as well as the body name, and then a number slider for the frame, connecting the repo path, and then another refresh. So before this, I'll have to run it again so that it can actually populate. And you can see we have our deformation still out of plane because of the one tendon that's being pulled. You can see some monitor points are off. We might need to adjust based on the indexes of the mesh. It's just snapping to the closest. But here by refreshing, you can then see these VTUs be represented in your Rhino viewport. If you bake it, however, you can see it looks quite messy, and that's actually because the VTU is not something that is typically worked with in Grasshopper, so the normals of the mesh are not aligned. Here we can unify the normals of the mesh using the unify mesh component, which is nice because, as you may not know, Rhino has its own renderer, so you could actually go through set material properties and have a render for any kind of figure that you might need to prepare. This is nice if you'd like to have some figure of some sort of desired motion, but you don't know how to deform your mesh accordingly. Having it to where you actually acquire that deformed mesh is quite useful. So regardless, now that we've done that and we're able to visualize it in Grasshopper with the data, we can go through and look at the tendons again. Here, maybe I don't want the cavity at all, but I would like to just pull the tendons. Here, I'm pulling 1 from 0, 5 to 10, and 1 just 0 to 10. And you can see here, because of the geometry and the meshing, it runs quite a lot faster. And then here you see pulling along that strain limiting layer, and then some asymmetry towards the end because for the protocol, I have it where it pulls both evenly and then pulls one more. And again, in the past, maybe you have to, if you wanted to change anything about your design, maybe you have to do it on the workbench. Here you can see understanding how the body is going to move, the trajectory that you desire, all being done in Grasshopper and SOFA is quite useful for getting you to a point to where you have much less trial and error for the fabrication itself. Here, I'll take a look at the project folder that I have. This is where everything is being output. These are those VTUs that the SOFA shape, the meshes that are being generated, as well as some of the monitored points, all the information, as well as the output, all is in this project folder that you define at the beginning. For the protocol, again, this is all just keyframed. So the times that you have, 0, 1 to 2 seconds, or in this case, 0.5 to 1, are all keyframed to the specific values that you're plugging in here. So here I have 0, 10, 10 for my cavity, so 0 to 10 kilopascals, and then 0, 20, 20, or actually I'll do 20, 10, where it's going from 0 to 20 millimeters of pulling the tendon back to 10 at 1 second. So here we see that pulling 1 with the deformation, pulling quite a lot, and then releasing it some towards the end. Again, you might see some deformed properties of your mesh. By refining the mesh or simplifying the mesh, you can have much better simulations. We now have this shape that deforms and follows that protocol with the output trajectory of that tip. So that's all for getting started on your first example. What I will do next is actually just walk through and point out some of the things that are unique about the Continuum example and the pneumatic gripper setup that we have in the examples that we provide. So to jump in, we will open up the example for the Continuum arm. Here you can find it in your cloned repository under examples, the respective GH file. And here, if you're opening for the first time, you'll notice the same errors as before. In the installation video, we go over, of course, how to set your 3 paths. Go ahead and set those and we'll jump in. You'll be able to see your sofa preview, all set up with the tendons and the tracked points for monitoring. All I'm doing here is just changing the window size again. So by clicking Run Sofa, we can see what's happening. The protocol I have here is pulling one by one each of the tendons, the same amount, so it sort of works its way through this workspace. In Grasshopper, we have these 3 tendons as well as a cylinder that we actually use for our body. We have the quad remesh, the same we did previously, so that we have a refined mesh for accurate movement. And here, to create these tendons, we have 2 expressions that are being used to construct the points. If we interpolate between them, we can actually see how they run through that cylinder shape. And those are being passed to the sofa tendon. Here, the only difference is that we have 3 channels, because here you can see we have these 3 trees. The data structure is very important to keep in mind as you go through all of the examples or your own creations. Here I'm pulling it by force, as well as I have pull points selected. Here in my sofa preview, you can see I've actually designated an area outside that I want to pull the tendons, and you can see that in sofa as well. For sofa body, not much here has changed. I have a body name associated with it. I have that cylinder body that's being plugged into the quad remesh. I have monitor points just going along the backbone, those pink dots that you see here. And notice the quad remesh is going to both the geometry and the visual geometry. Here, because we are only working with the one body and no cavities, I'm just working with this one mesh. I have my Young's modulus, my Poisson ratio, mass, and mesh size all defined going into the sofa body. I also have a fixation, so here, just having a place towards the base of the cylinder so that when I have gravity enabled, it will not just fall in open space. Here, of course, because we have these number sliders defining everything, we can adjust them. For example, the tendons, these 2 expressions also allow you to define some twist. Here, as I slide this number slider, the tendons then change the way they're wrapped through the Continuum arm. And if I run again, you can see immediately I'm able to test out this new iteration. So the same protocol for pulling the tendons, but now I have vastly different performance because of the small helical twist that I've enabled to the tendons. These 3 channels for the tendons are, of course, also plugged into the tendon profiles where I'm sending the keyframed data. And here for time, I have it going 0 to 0.5 to 1 seconds for that first tendon. And here you can see that entwined data structure to create a tree, which aligns with the force that I'm pulling. So I'm pulling 100 millinewtons for each one of these. And my profile goes into my sofa scene component, controlling that body as long as the channels align. In the camera positions, I've just selected the same way I did in the previous example, where I look in my Rhino viewport and select them manually. Keep in mind, you can also export a view file from sofa itself, but using that sofa preview and those points is really helpful in creating your environment. Now notice I have a Boolean true to the sofa scene, like I've said before. Next, getting into the results, here you can see the tracked points that I've selected to monitor throughout the movement. I've also taken the last index, like I did before, to see just the tip movement as it goes through this protocol, and even connected a convex hull for visualization. Here I also have an export shape to my sofa body of 10. So scrolling through those frames, I'm able to see my Continuum arm deform in real time. Keep in mind these VTU files are exported to your project folder, as well as the meshes. Here we have the visual. Here we have the monitored points, the output for the cables, as well as those shape VTUs that I mentioned before. So these you could use in any kind of visualization that uses VTUs. Here in the sofa shape, we're able to immediately see that in real space. And with this as well, we can visualize that tip trajectory. Here, I've not yet refreshed it, so it's still old, but by pressing on that Boolean, then it can update, and I can see how that shape deforms according to the workspace. And here, again, just seeing the full monitored points as the trajectory continues. Now, the sofa scene that's created is actually also in your project folder as a scene.json, and you can see this is where, if you're familiar with sofa, you'll be able to see all of the variables that are passed in, such as the monitored points, the cables, and everything about your body, so that this scene in sofa can actually be constructed with the respective meshes. The gravity I have not hooked up, so gravity is working. The floor I have not hooked up, which means that there is no floor. In our next example, I will have a floor with gravity as well. So here, just going and twisting more. Again, this is a tool used. I can even change the tendon offset and easily visualize what that looks like. Here you see much different movement, even though it has the same protocol, pulling those 3 tendons in series. And I could also look at different examples, pulling different ones in parallel. But here I can refresh that trajectory and see it in real time, as well as the sofa shape, where in this case, it's much less prominent as this buckling occurs with these helical tendons. And again, all of these tendons are from this parametric workflow, creating these 2 expressions, having the monitored points, and putting it all together in our cushion environment on the Grasshopper canvas. Now for the final example, we will be opening the simple gripper, which is again in the repository examples folder. Once that's open, we go through the same initialization as before, making sure to set your 3 folders. Once those folders are set, you can go ahead and see the preview. Now I will say, for this example, this requires Pufferfish for the reduce mesh component, simplifying the quad remesh that we had from before. And that's just for the entire process to run faster. So we can now click run. So in this example, we see that we actually have 2 bodies that are deforming to grip a object. So jumping into the script, we have everything parameterized. Within this create PneuNet example, we can see something similar to what we had before, where we have many expressions and equations going to create the geometry. And then we have this graph mapper. So this graph mapper component, as I slide it, you can see that I actually changed the profile of the PneuNet. So having chambers that are wider at the base versus the end. This can be applied for a parabolic form, and many others we'll get into later. From this create PneuNet, you can see I actually have B-reps and boxes that are coming out of it, where if I attach it, I can see exactly what the cavity looks like, as opposed to the body or the strain limiting layer, as well as the fixation plate just at the front. Additionally, I can throw down a points component to see what kind of points I'm monitoring. So just monitoring points along this PneuNet here. From that is where I do all of this meshing. You can see I have some triangular meshes generated here for the cavity as well as the body, as well as have a mesh for the strain limiting layer that I'm passing into the region. Now from that, you'll see that I actually have two bodies. Now I'll first go through the first one, which is the same that you would do it before. The main thing that is different here is I have to introduce a collision mesh. If I actually look at how these PneuNet actuators work, works along this interaction between the faces of the chambers. So here all I'm doing is I'm indexing all of the faces which I'm interested in the contact, either between the object or self-contact. So you can see just those faces there. I merge them together and then go through my same meshing process, simplifying the mesh with the pufferfish component. And that is fed into the collision geometry in the sofa body. All my parameters are over here, and my body meshing is going both for the visual and the geometry. The cavity is coming from the tri-remesh I had from the cavity, and the region for the strain limiting layer. Now, something else is the protocol. So in our previous examples, we had our objects completely static, just having the actuation occur. Here, if you notice when I run, the actuators themselves are lifting up as the protocol goes on, and that's what I've defined here. So the same way I keyframe my pressure protocol or my tendon protocol, I'm just saying from 0 to 1 second, I want it to lift up a certain amount, just putting in the Cartesian coordinates for that protocol. And I can match the keyframes here. And here you can see I have from 0 to 0.5, positive pressure, and then going to 1, I have negative pressure. The last two that are new for these is you might notice that the actuator was on its side coming out of that create PneuNet. Here, I actually just have transformations for both rotation and translation. And these are just vectors that you pass to move and reorient the actuators. So because I wanted them in this vertical orientation for grasping, I have respective rotation and translation for both of those bodies. And in the preview, this is what you can use to really confirm that those orientations are correct. So going from this flat to this oriented approach, just finding those transformations that are valid for what you desire, plugging those into the rotate and translate. Now here you'll notice I have two body components, and the main things that are changing are the orientation. Here I have the pressure profile. I actually have those two body components merged into one, passing into a singular sofa scene component. And then the last thing that's new is actually defining a target. So here I have a sphere that I want my gripper to pick up. So I'm just going through the same process of taking the B-rep, using a tri-mesh on it, and then using the pufferfish component reduce mesh so that it doesn't have to calculate the collision at a very high fidelity mesh. And here, if I visualize my collision model in SOFA, you can actually see what that looks like for both the target as well as that reduced collision mesh I made, only selecting the certain faces of my PneuNet. Again, when it actuates, the reason for the bending is actually these cavities that are adjacent to each other, expanding and contacting each other. So anytime you are working with a target or anytime you're working with something where self-collision matters, make sure that you add in that collision geometry. If you see that you don't have the desired actuation you want, most likely you will have to look at the meshing. I also have the camera set up so that we have this sort of head-on visualization. Again, working with SOFA Preview is the best way to get this if you don't want to make a view file from your SOFA scene itself. Additionally, you'll notice that I have a collision model for the floor, and that is because I've put in a 0 for my floor height, and gravity I've leave at default, so everything is going down in the Z direction. Now here, all I'm doing is running again with my repository folder open, and here you can see my VTUs generate as the simulation runs, which are used for the export shape at the end. And just by changing that one integer, you can change how many frames are in between each visual body. So for the results, I have only one of my fingers' body names attached for the points. And you can see with that, I'm able to have two separate sofa shapes to see the reconstructed motion of the gripper. Something else I'd like to say is that you can also extract the contact points from the sofa results between the finger and the target of the sphere in this case. So with everything being said, thank you for watching. Feel free to comment with any suggestions or comments or what you'd like to see more of. For now, that concludes our Getting Started tutorial, and be sure to stay updated on the repository, as in the future we will be making changes and updating as time comes. And I hope to see the soft robots you design using Cushion.